back. It's time to prove that some integrals exist. We've defined the Riemann-Stieltjes integral this way. It's a limit as a partition norm approaches 0 of a sum that looks like a Riemann sum. And today we want to address this question: what conditions guarantee that a Riemann-Stieltjes integral actually exists? Because it's a limit, it can fail to exist for some functions and for some curves gamma, and it can exist for others. And so we want to add some conditions, and we want to prove theorems that under certain conditions, this integral is guaranteed to exist. So the first condition that we have is a length condition on the path gamma. Now, it's natural to expect that we would need the path gamma to be continuous. If the path gamma just bounces around all the different points on the plane and has no rhyme or reason to it, then that's a fairly bad situation, and we wouldn't expect the integral to necessarily exist. But continuity is actually kind of a weak condition when it comes to trying to guarantee a total measure small. There are continuous paths that have as their image an entire two-dimensional square or an entire disk. There are continuous paths that have infinite length by any reasonable measurement of length. There are infinite paths that follow fractal patterns in the plane. And integrals on such paths, well, they may exist, but we wouldn't expect easy conditions to guarantee that such integrals exist. So basically, what we need to do is we need to start with a finite length condition. Now, let's look at this condition. This is going to be the condition of bounded variation. But first, we're going to define the variation with respect to a partition. So let's let gamma go from AB into the complex plane. And let's let P be a partition of AB. Now, as usual, the partition will have some cut points ti and also some sample points tau I. Whether P has the sample points or not, whether it's a tagged partition or not, we don't care because we're not going to use the tags tau I in this definition. But so we're going to use the partition to define the variation. So the variation of gamma with respect to P is defined to be, it's the summation I equals 1 to m, that is for the number of points ti of, that'll be gamma of ti minus gamma of ti minus 1. And then if we just write that, then the sum will telescope and end up being gamma tm minus gamma t0. But we're going to put a modulus there, and that'll be the variation of gamma with respect to P. So that might look like a strange definition, but that's a perfectly reasonable definition if you think of it correctly. So we have the interval, let's draw this horizontally. So we have the interval from A to B here, and we have a path gamma that maps the closed interval from A to B into the complex plane. So this is going to be my picture of the complex plane. Here's R, here's IR, and then we have gamma of A, and then we have some sort of behavior here, and we end up at gamma of B. So the path is some sort of map, and this is the image of the path in the complex plane. Now, if we have a partition, then the partition gives us a sequence of points ti in the domain. So it gives us a sequence of dividing points here. And then, and including this will have to be one of them, and this will have to be one of them. So on the basis of these dividing points, we get a sequence of waypoints along the path. And then we can approximate the length of the path by drawing straight line segments between the waypoints. So the path is curved, but nevertheless, we can connect the waypoints by straight line segments. And we'll get a diagram that looks something like this. So this is a piecewise linear or a polygonal approximation to the shape of the path gamma. So you come along this just following straight lines between them. Now, those straight line segments are all finite straight line segments, and so they all have lengths. And their lengths are given by this formula. Gamma ti minus gamma ti minus 1 modulus will calculate the difference between these complex numbers. And then the difference between these complex numbers, the length or modulus of that will give us exactly what we want. So this variation, subject to the partition P, is merely an estimate to the total length of gamma. And from the picture, you would expect it's an underestimate for the total length of gamma, right? Now, it's hard to define the length of gamma directly, but that's basically what we're doing here. We're defining an underestimate approximation to the length of gamma, and then we're going to define the length of gamma, although we won't call it length. We're going to define the variation gamma to be the supremum of all possible values you could get this way. So we're going to take the supremum of every possible value that could be approximated this way. And the idea is when you get more and more and more points here, then you get closer and closer and closer approximations to the length of the path. And so the supremum of all of these values will be the true length of the path. So the variation of gamma is defined to be v of gamma, and that's not with respect to p, but just, period. That's the supremum over all p. I'm not going to write it out here, but this is the supremum over all partitions of the domain of gamma, of the variation of gamma with respect to p. So basically, cut this path into waypoints however you like, and connect the dots between the waypoints and measure the total length of those waypoints, and then take the maximum possible or even the supremum of all of the values of the total length that you could get that way, and that's what we call the variation v of gamma. Now, that's a supremum. It's a supremum of a whole bunch of values. These values have to be finite, but the fact that the values are finite doesn't necessarily mean the supremum is finite. And indeed, this can be infinite. That's kind of the case that we want to exclude if we want our integrals to be nice. And so we define the path gamma to be a path of bounded variation if this is finite. So if v of gamma is not infinity, we call gamma bounded variation. Now, you might think that bounded variation is similar to continuity, and I suppose they're related, but they're not the same thing. A continuous path doesn't have to be bounded variation, and vice versa. A bounded variation path doesn't have to be continuous. A path could start off at a value, and then it could hop to another value, but do nothing else particularly strange. It could have a jump discontinuity here. There would be a variation here that we could measure as the distance between these 2 points. And when you calculate the total variation, you would get a term in there corresponding to the length of that jump, but it would still be finite. Now, if it's a crazy discontinuous path that does all kinds of this crazy stuff, then it would probably have infinite variation. But if it simply has 1 or 2 or a finite number of jump discontinuities, then often we still have a bounded variation path. And that's convenient if we're trying to break an integral into finitely many other integrals, and we might be introducing jump discontinuities. It's convenient to know that we don't have to then exclude that as not the kind of integral that we can calculate. So a few jump discontinuities are really not necessarily a problem when it comes to bounded variation. So let's talk about the relationship between the variation with respect to P and the variation with respect to Q if Q refines P. So I'm just going to state this. I think it's geometrically obvious here. So here in blue, I've represented a partition P. And I want to go in pink and represent a refinement of this partition by adding a few more points. Okay, I'm just going to add 3 points because I don't want to clutter the diagram too much. I'm just going to add these points. And now the use of color is a little bit hard here. You have to remember that a partition is refined by another partition if the refining partition has all of the points of the original. And so these points in blue, you have to sort of also regard them to be pink. So what we've done here is we've added a couple points in between the second and third, which is here and here. And we've added a couple points, not in this next branch, We've added 1 point over here. And so we get a competing length, the variation of gamma with respect to this new refined partition Q, and that would look like something like this. So if Q refines P, then it has all of the waypoints that P does, plus possibly some more. And that means that in some circumstances, we may be taking the same straight line path from a point to another point. But in some other circumstances, we are not taking the straight line path from one point to another point, but some other more circuitous route between those points. Now, the straight line is the shortest distance, of course, and that means that the calculation of the distance that comes from P, from this term, the distance from here and the modulus of it, is going to be less than or equal to the distance that comes from all of those little straight line segments that I've represented in pink there. And that's just sort of a rough geometric proof of a general fact about the variation of these paths. And let's state that officially here, proposition. So if P is refined by Q, if there are two partitions of the same interval AB, but one refines the other, then the variation of gamma, with respect to P is going to be less than or equal to the variation of gamma with respect to Q. And that means that the variation of gamma with respect to the partition is an increasing function of the partition. So i.e., variation of gamma with respect to whatever is an increasing function of P. It's a function that takes partition's input and gives real numbers output, and non-negative real numbers, because these are all non-negative reals in the sum. And it's an increasing function. And because it's an increasing function, then we can conclude that if it has a limit, that limit is its supremum. So the corollary of this, and we prove this generally about limits and suprema of functions defined on partitions. So the corollary of this is if the limit as the partition norm goes to 0 of the variation with respect to P exists, then it equals the supremum. And we prove this as in general about functions that are increasing functions in this sense. So it equals the supremum. Now, what is the supremum of this? It's by definition the variation of gamma. So it equals the variation of gamma. So if you are so lucky that you can calculate this limit, then that limit must actually be the variation of gamma. And so that's a convenient little property to know about variation. It can help you prove this, that a path has bounded variation, because you can just calculate that limit. All right, next we're actually already ready to prove our main theorem of this section, which is the theorem on existence of integrals. The integrand function f needs to be continuous, and the path gamma needs to be bounded variation. Now, I'm not saying that's an if and only if. I'm saying if those conditions are met, then at least under those conditions, then we can be guaranteed that the Riemann-Stieltjes integral exists. So let's do a statement of that. If f is a function from the interval ab to c, and gamma is another function from the interval ab to c, if f is the integrand and gamma is the path, if f is continuous and gamma is bounded variation, then that integral will exist. That's what we're trying to show. Now, the integral, of course, is by definition this limit. It's a limit of this function, which is a function of the partition. And we've already done all of this investment to show that if a function defined on the space of partitions is a Cauchy function in the sense of, as a function on partitions, it's Cauchy, then it will have a limit. And so the reason we went to all of that effort to prove that was because we need to show now that this limit exists. And now we have that tool at our disposal. We can prove that this integral estimate as a function of P is Cauchy. So that's going to be our strategy. We're going to take that integral estimate and show that it's a Cauchy function. So let's write that first. So we'll show that well, this thing, the summation f of tau I, gamma ti minus gamma ti minus 1, summation I equals 1 to m. This thing, which is ultimately a function of p, so is a Cauchy function on partitions. And so we've already shown that a Cauchy function must have a limit. And so that will be sufficient here. So that's the strategy. So how does that strategy work? We need to pick, well, we need to demonstrate what does it mean to be Cauchy. For every epsilon, which is how close you want to get, there must be a delta, which is how fine the partitions need to be, so that if P and Q are two different partitions, both of them delta fine, and P is refined by Q, then the difference between this function on P and this function on Q is going to be no greater than epsilon. That's what we need to demonstrate. So of course, we're going to start by letting epsilon be greater than 0. And now I immediately need to tell you what delta is. Who the heck knows what delta is? So what we need to do is, this thing has an f of tau in it, and we need to manage the possible variability of the function f first. Now, we can do that using the continuity of f, but continuity is not enough here. We need absolute continuity, sorry. We need uniform continuity of f on its domain. Fortunately, its domain is compact and the function is continuous, and so f is uniformly continuous. So f is uniformly continuous on the compact set AB. Because it is a continuous function on a compact set, it is automatically uniformly continuous. So it's uniformly continuous on this. And so we're going to choose delta for epsilon, no, not for epsilon over the variability of gamma in the definition of uniform continuity. So what does it mean? What does uniform continuity mean? It means for every epsilon, there exists a delta such that for any 2 points x, y, if x, y are delta close, then f of x and f of y are epsilon close. So what we're really choosing there is we're choosing a delta so that whenever x and y are delta close, then f of x minus f of y will be no farther apart than this, my new favorite number, epsilon over the variability of gamma. And if this seems like a magic number coming out of nowhere, that's because that's a magic number coming out of nowhere. And that's because that's the number that will work in the proof and cancel a term later of the variation of gamma that will come up. The definition of uniform continuity says for every epsilon, there must be some delta. And so all I need is that this is a positive number. Now, notice here that I have implicitly used the bounded variation of gamma already in this proof. I'm obviously using the continuity of f, but maybe it's less obvious that I'm using the fact that gamma is bounded variation because I'm dividing by the variation of gamma, which is sort of presuming that that's a number, right? It can't be 0. Actually, if the variation of gamma is 0, everything is trivial. And so let's just assume that the variation of gamma is not 0. So we're dividing by this. It's a positive real number. And we're taking for granted that it's not infinity, so we don't have to worry about that. So so we're going to choose delta for that value in the definition of uniform continuity. And then what are we going to do? Well, that's delta. And then, so we're trying to show Cauchy, right? So for any epsilon, there exists a delta such that for any 2 partitions, so let's choose 2 partitions with a refinement relationship. So let's let P and Q be partitions. And let's assume that the norm of P is less than delta, and the norm of Q is less than delta. Oops. Norm of Q is less than delta. And furthermore, that P is refined by Q. This is actually redundant. Once it's refined by Q, it will have a norm less than delta, but it doesn't hurt to say so. Okay, so those are the 2 partitions that we need here. Now, I want to draw this situation because it's important for us to be picturing the right thing when we're picturing partitions refining one another. So I want to make a simple case, and a simple drawing is going to be worth a lot here. So here's A, and here's B. And the partition P is going to be represented in blue in this drawing. So P is going to be in blue. And this will be one of the points of the partition P. And I want to highlight that it doesn't have to be evenly spaced. And so P is going to look like that. Okay. So here M is going to be 4, right? That's T0, T1, T2, T3, and T4. Obviously, this is not the general case. Oops. T0, T1, T2, T3, and T4. Now Q is going to be represented in pink here. Q is going to refine the partition P. Now Q must have, if it's going to be a refinement of P, it must have cut points at all the same locations. But we're not going to call them T0, T1, T2. We're going to call them S0, S1, S2. But if it's a refinement of P, then it's allowed to have a few more. Now I don't want to go overboard here. I want this proof to be as clear as possible. So I'm going to add one here, and another here, and another here. And then I'm going to label them. Notice that the labels then go out of sync, right? This is now S3, and this is T2. This is S4. So the indices go out of sync when this happens. This is S5, and this is S6, and then that'll be S7. So some of these are equal to the values in the partition P, and some of them are unequal. Okay, so this is the general situation if we have a partition refining another partition. And if these partitions are delta fine, then I suppose in my picture, delta is a pretty big number, right? It's bigger than any of these distances. So I mean, sort of long term, when you're thinking of epsilon as a very small number and thinking of Q as a very small number, then you should be thinking of delta being really small, and these things are really, really fine, but then you can't see the picture. So this is like the intellectually useful picture, not the picture that represents what's happening long term in the limit. All right, so we need to calculate this function on P and this function on Q, and then we need to subtract, and then we need to try to claim that the difference is small. So let's consider. Hopefully I have room for this. I'm going to evaluate this function on Q, and I'm going to evaluate this function on P, and I'm going to subtract. And I'm not sure whether I want the Q version minus P or P minus Q. It doesn't make any difference. Let's do it on Q first. So we're going to take the summation. Let's do J. Summation J equals 1 to N of F of sigma J times, not F, but gamma of Sj minus gamma of Sj minus 1. That is the function applied to the partition Q, right? Whose cut points are the S's and whose sample points are the sigmas, which I haven't shown. But I may need to show them eventually. So let's assume that we have some sigmas in here. This will be sigma 1. And then here, this would be sigma 2. And then here, this would be sigma 3. And we also have some taus in here. This will be maybe some sample point tau 1. And then we'll have some other sample point tau 2, etc. So this is the function evaluated at Q. I need to subtract the function evaluated at P. I'm going to use a different indexing variable. I goes from 1 to M here. And then I'll get F of tau I times gamma of, not S, but T sub I, not tau either, can't write, Ti minus gamma of T I minus 1. All right, now this is the function evaluated at Q. This is the function evaluated at P. The definition of Cauchy means I need to prove that this difference is small. In particular, this difference has to be epsilon small. It has to be less than epsilon. So actually, I'm not going to assert that it's less than epsilon. I'm going to try to eventually prove that it's less than epsilon, but I'm going to put this less than epsilon to indicate like that's my goal. That's what I'm going for. I'm trying to calculate that this is less than epsilon. Okay. Now, this is a summation and this is a summation, and they have different indices, and they're multiplied by different values here. And so there's a pretty big challenge to combine these summations into one summation. This summation, gamma ti minus gamma ti minus 1, is in some cases, so in some cases, gamma ti minus 1 is exactly equal to gamma sj minus 1 for the right choice of j. In some cases, it's not equal to that, but it is equal to a sum of differences. So for example, gamma t1 minus gamma t0 is not gamma s3 minus gamma s2, and it's not gamma s1 minus gamma s0, but it is the difference between these two gammas plus the difference between these two gammas plus the difference between these two gammas. In other words, for example, just as an example here, gamma of T1 minus gamma of T0 is equal to gamma of S3 minus gamma of S2 plus gamma of S2 minus gamma of S1 plus gamma of S1 minus gamma of S0. The reason this is possible is that between T1 and T0, both of them have to be S sub something. And so this difference between gamma here and gamma there has to be somehow a sum of several distances between gamma of S something, but not the same something, right? What about the taus? The taus don't have to be equal to the sigmas at all. There's no requirement that the taus and the sigmas are even related when we talk about the refinement of a partition. So in my picture, it seems that tau 1 and sigma 2 might be equal, but I don't mean that they have to be. So what we would like to do then is leave this summation alone and open up this summation so that it is actually a summation indexed by j and summing over the s's. So I'm going to do that kind of wrongly first, and then I'm going to point out what's wrong and fix it. So basically what we're doing here is I want to use the fact that each of these differences between ti and ti minus 1 can be expanded as a difference between the s's. So if we just had this summation, this is what we would do. We would say this is equal to, this term just gets copied, nothing happens. Gamma sj minus gamma sj minus 1. So nothing happened to that term. Then this is now newly going to be indexed by j. And instead of summing the differences gamma tau I minus gamma tau I minus 1, I'm going to peel apart each of these as a sum of differences between consecutive j's. And I'm going to get gamma sj minus gamma sj minus 1. Now, here I have to multiply by f of tau I. And now, I mean, that's sort of correct. The only thing wrong with that is this term doesn't make any sense. Basically, yes, f of tau 1 times the difference between gamma t1 and gamma t0 is equal to the sum of the values f of tau 1 times this difference, f of tau 1 times this difference, f of tau 1 times this difference, because those differences will telescope and cancel. Yes, but now I've got f of tau I written inside a sum indexed by j. Okay? So that doesn't kind of make sense, right? So this needs to be expressed in a way that makes it depend explicitly on j. And here's what I'm going to do. I'm just going to say that this is f of tau I for some I, and that I itself will depend upon j. And so what I'm going to write here is this is f of tau at some index I, but I don't know which one, but that index itself will depend upon j. So when j is 1, then we're looking at this difference, then I sub j will be 1. When j is 2, we're looking at this difference. I sub j will also be 1. When j is 3, we're looking at this difference. Tau sub I sub j will be tau 1 again. But when j is 4, now we're looking at this difference, which is made up out of this difference, then finally we'll be looking at tau sub 2. So in this example here, let me write this in blue and in pink to illustrate the point. So tau sub I sub 1 is tau 1. Tau sub I sub 2 is tau 1. Tau sub I sub 3 is tau 1. Tau sub I sub 4 is tau 2. Tau sub I sub 5 is tau 3, and etc. So basically we are, in some way or another, the tau value, the index of tau that is right for any given term j here depends upon I, and that's what I'm writing here. Okay, so by some reindexing, we can get this to work. Now, the point of this was so that these sums can be combined, of course. Notice, however, before we combine them, here, this may look like an alternate integral estimate for the partition Q, because it's indexed the way the Q sum should be indexed. However, this is not a valid integral estimate with respect to the partition Q. And the reason it's not valid is that the sample points tau sub I sub j do not always fall within the intervals from sj minus 1 to sj. They don't obey the right inequalities. So when j is 1 in this sum, we're actually looking at this interval, but tau 1 is outside that interval. And then here we're looking at this interval, it's inside, okay, but then when we look at this one, then it's outside again. So here, because tau sub I sub j is not always between sj and sj minus 1, because of that, then this is not actually a valid integral estimate for Q. But it doesn't matter, we're just trying to recombine our sums here. So that's one point you should notice. Another point you should notice is, although it falls outside this interval, it can't fall too very far outside that interval, because we've assumed that the norm of P is less than delta and the norm of Q is less than delta. And all these original big intervals between the T's are size less than delta, which means that how far outside the interval it actually falls is bounded by this delta, right? It can fall like outside these things, but not farther than delta away from where it sort of ought to be. Okay, so with that reindexing in mind, now we can join these sums. So we're going to join the sums. Let's see, how many steps do I want to do at a time here? Let's do things step by step. So the first thing that we're going to do is simply join the sums. We're going to get summation j equals 1 to n of f of sigma sub j, gamma sj minus gamma sj minus 1, and then minus f of tau sub I sub j times gamma sj minus gamma sj minus 1. And then absolute. Okay, so everything here is inside the summation now. And notice this term matches this term, so we'll factor it out. So absolute, I said absolute, but that's modulus. So modulus sum j equals 1 to n of, what do we get? F of sigma sub j minus f of tau sub I sub j. And then times gamma of sj minus gamma of sj minus 1 modulus. Now notice that these are basically the values of the function f sampled at two different points. These are the proper sample points for the partition Q, which are in pink, and these are kind of like, I don't know, splitting it by the partition Q, but still somehow obsessing over the sample points for the partition P. And they're sampling the function at different points. But we will have some control over how far apart those points are. I notice we have the, I pointed out they're less than delta off from where they should be. So the next thing we're going to do is triangle inequality. We're just going to split, we're going to push the modulus across the sum and across the product as well. So let's do that next. So this is going to be the summation j equals 1 to n of modulus f of sigma j minus f of tau I sub j, and modulus, and then begin modulus gamma of sj minus gamma of sj minus 1. That looks good. Okay, so this is now, we've just triangle inequality. So that's by triangle inequality. And then this thing we've controlled. That is exactly why we did a significant amount of the work before. We've chosen delta for this value in the definition of the uniform continuity. And the x values here are less than delta apart because they both come from, so for any given value of j, sigma sub j and tau sub I sub j both come from the same interval, like here, or here, or here, or here. And those intervals have a maximum size of delta. And so because those intervals are under control, then, and because we've chosen delta for this value in the uniform continuity of f, so because we have that level of control, this thing is no more than epsilon over the variability of gamma. So I'm going to bound this thing, each one of them individually, I'm going to bound by epsilon over the variability of gamma, and then factor it outside the sum. So this will give me epsilon over v gamma summation j equals 1 to n of this thing, sj, gamma sj minus gamma sj minus 1. Now here we have epsilon over the variability of gamma, and here we have, this is nothing more than the variation of gamma with respect to the partition Q. So let's write that. This is epsilon over the variation of gamma times, this is exactly the variation of gamma with respect to the partition Q. Now, the variation of gamma is a supremum of terms that looks like this. And so this term here can't be larger than the denominator. And so that's going to be equal to, that's going to be less than or equal to epsilon. And now I notice there's a little, I don't have any strict inequalities here, right? I'm supposed to follow the definition of Cauchy exactly. One of these should be a strict inequality. And so let me see. I have been a little careless with the signs here. These are all true equalities. This one is a triangle inequality. So this one should be less than or equal to. And then this one, when I replace this thing with this, that should be strictly less than. So that's going to be less than epsilon over the variation of gamma. And so we'll get, ultimately, this thing is less than epsilon. So the difference between one term, and so the difference between the function applied to P and the function applied to Q is less than epsilon, provided that we have a refinement relationship between them. That establishes that this function is a Cauchy function on partitions. And if it is a Cauchy function on partitions, then it must have a limit. And the limit is by definition the integral. And that demonstrates that the integral exists.